Hey, this video clip goes with the section on Raoult's law, 11 point. Oh yeah, it's 11.4, I think, in your textbook. Let's start with the question: does water evaporate easily, quickly, or is it difficult to evaporate as compared to other liquids? And if you've ever stuck around to watch a glass of water evaporate, I'd like to talk to you because I never have. It just takes forever. So compared to other liquids, certainly water evaporates very slowly. And that's one reason why if you spill a little bit of rubbing alcohol on your skin, it feels cold because it evaporates so quickly as compared to water. And evaporation is a cooling process, and that takes energy away from your skin because the alcohol evaporates so quickly. Does water at normal conditions have a relatively large vapor pressure or a low vapor pressure? Well, if you think back to maybe chapter 8, I think it is, I'm not sure, you know that that vapor pressure is a measure of how easily something evaporates or vice versa. And so since it evaporates very slowly, water has a very low vapor pressure. The pressure above the water due to the water vapor is low. Of course, the warmer you make the water, the more the vapor pressure builds. But how does the vapor pressure of sugar water compare to the vapor pressure of pure water under the same conditions? Good question. So if water evaporates slowly, how does sugar water evaporate? Slower, faster, the same? Answer: slower. In some way, the particles of sugar get in the way of the water evaporating. So the vapor pressure above the sugar water is even lower than it used to be. Here's a, oh goodness, let me see if I can shrink this down to a smaller size so we can see it a little bit better. Smaller still even. A couple of containers of liquid sealed off so that we can measure the pressure above them. In the left-hand chamber I have pure solvent and I have certain vapor pressure. Call it water if you want. These are the gaseous molecules in liquid. But over here I see they've cartooned in some sugar or some other solute that sort of gets in the way. We call it a non-volatile solute that doesn't evaporate itself very easily. Most usually a solid, could be a liquid, as long as it doesn't evaporate and get in the way much up in the airspace. But here I count 6 cartoon particles. Over here I had 2, 4, 6, 8, 9 or so. So the pressure up over the pure solvent is larger than the pressure of the solution, and that's always true. Solute particles occlude, interfere with, get in the way of the evaporation of the... Oh, I said that incorrectly. I need to change that. When I put the PDF online, I'll change this. The solute particles occlude the evaporation of the solvent particles. That's a solvent. Holy moly. Change that to solvent. I'll change it before I post it. So here's a crazy thing that happens. You take a jar, you put a water beaker and a sugar water beaker or salt water or anything. It doesn't matter what the solute is as long as it itself doesn't evaporate very easily. And if it's true that this one evaporates slower than this one, then this beaker, in a way, the liquid level gets lower and lower and lower and lower faster than this one. The water particles get up into the airspace. But because of another factor, an interesting phenomenon, these water particles that escaped up into the airspace up here actually then end up crawling into this solution trying to water it down. So that if you wait long enough, all the water will evaporate from here, and I'll have this airspace saturated with as much water vapor as it can hold, but that water will eventually make its way over into the right-hand beaker, trying to, in essence, water down that concentrated solution. Here's a graph that speaks to that. On the x-axis, the mole fraction of solvent. So if I had only pure solvent, the mole fraction would be 1, pure solvent. And that's the vapor pressure originally of the pure solvent. But if I had no solvent, well, then I would have no vapor pressure. If I just had solute of some kind that was not volatile or evaporating, and in between they're connected by a straight line, and that straight line is indeed the mole fraction of the solvent. It's also the slope of the line. Rise over run, rise over run. And on this axis, the pressure of the solution, the vapor pressure of the solution, or the vapor pressure above the solution. And we can word that like this, mathematically. And it's called Raoult's law. Make this a little bit bigger. Called Raoult's law. It says that the vapor pressure above a solution is equal to the original vapor pressure of the solvent times the mole fraction of that solvent. So if I had a pure solvent, no solution, this would be a 1, and they would be equal. But of course it's not, otherwise why would we talk about these mixtures? It's called Raoult's law. Example, the vapor pressure of water at 25 degrees Celsius, room temperature-ish, is 24 torr. Not very much. Doesn't want to evaporate very quickly. What if we mix 39 grams of a solid white chemical, ammonium nitrate, in with 200 milliliters of water? Well, if it was just the water, I'd have this vapor pressure. But it's not just the water any longer. That 200 milliliters of water is now occluded, interfered with. The surface of the water, not in as intimate contact perhaps with the space above. What's the new vapor pressure? I say, let's find the mole fraction. Because Raoult's law says I should know excuse me, the mole fraction of the solvent. So I had 39 grams of ammonium nitrate, change grams to moles. I had 200 grams of water, 200 milliliters of water, change grams to moles. So I have 11-ish moles of water and only a half a mole about of that ammonium nitrate chemical. So the mole fraction of water is 11 divided by 11.1 plus about 0.5. So the mole fraction is less than 1, not much less than 1, but still less. So the 24 won't be 24 anymore. It'll be a little bit less, down to 23. 3 sig figs. And I'll say it again. A pure solvent has the mole fraction equal to 1 and no reduction in the vapor pressure. But since the mole fraction of the solvent is less than 1 in a solution, then I have my vapor pressure above the solution being less than the vapor pressure of the original solvent. I don't know if that makes any sense until you study it or try a few, practice a little bit. Here's another twist on Raoult's law and vapor pressures and such. I may have to shrink this down so you can see it a little bit better. Here's another container with 2 volatile solvents, or I don't know if they're 50-50, if they're evenly mixed. How do you define solute and solvent? And the answer is, I don't know. The utility of the definition, in a sense, loses import. So here's a mixture of blue and pink particles. Maybe it's about 50-50. Even though the mole fraction is 50-50, 0.5 and 0.5 mole fraction, 0.5 and 0.5, if they can both evaporate, they both get up into the airspace. But because of other factors, particle forces and such, one of them might evaporate more easily than the other. So here's the deal. I measure the relative amounts. Maybe it could be these are both 50, 0.5, 0.5, or 0.45 and 0.55, who knows, something like that. And I know my original vapor pressure of my solvent A, or my compound A, let me call it. Or I could call this a solvent and solute. It doesn't matter which one you call which. They interfere with each other equally. They occlude each other. They interact with each other similarly. Let's see. I said, let's see, A, pink A, 1, 2, 3, 4, 5, 6 A's and 4 B's. So yeah, indeed, it looks like A evaporates a little bit more easily than B. But on the other hand, each substance, B occludes A and A occludes B. And so here at the surface where the liquid gas equilibrium is established, I'll have still more A and less B, but they're in a way they're getting in the way of each other's evaporation. So my A will come down, my vapor pressure of A will come down, my vapor pressure of B will come down, and the total pressure in this chamber, as measured by these little cartoon weights, will be this. Let's try an example. Let me enlarge this a little bit. So, example, I have room temperature ethanol, alcohol. It evaporates pretty easily. It feels cold in your skin. And also, if you've ever spilled nail polish remover on your skin, you'll notice that also feels colder, and that's acetone. So I have 100 grams of alcohol, evaporates pretty easily, as measured by this number. I have 100 grams of acetone, evaporates even easier. Oh my goodness, 184.5 torr is the vapor pressure there. Question, in that mixture, what's the total pressure above the solution that we create? We should imagine no other gases in the space above. Oops, too far, too fast. And so what do I need to know? I need to know something about mole fractions. To get mole fractions, I need to know something about moles. So here's my 100 moles of alcohol. Change grams to moles. Oop, there should be a little G there. I should fix that as well before I post this. Sorry. 100 grams of acetone. Change grams to moles. 1.7-ish moles of acetone. 2.1-ish moles of alcohol. Then I go and I find the mole fraction of each in the container. Alcohol, acetone. This plus this in the denominator is the same as 3.8924. By the way, these both add up to 1, so I could have easily got this number by just subtracting this from 1. 1 minus this should give me this, but I was being silly. All right, and finally, the pressure of the ethanol would be the original vapor pressure of ethanol times that mole fraction of ethanol, that 0.5576. Sometimes I put a little subscript number saying that's not significant, but I'm not going to round it off yet until the very end. So I'm pretty sure my ethanol would have a pressure of 24.48. My acetone, similarly, here's the mole fraction of acetone, and the vapor, this was given to me as well, and this was given to me. I had to figure this one out and figure this one out. But I see now my pressures have come down from 44-ish and from 184-ish, and my total pressure would be about 106 torr.